So today we are going to start a new topic. All right, everybody. Today we are going to start a new topic. It's called structural dynamics, and it's a little bit different from any dynamics course. Like typical dynamics course, they have only dynamics of particles and liquid bodies. This course is a little bit special. We add some other dynamics part. So usually structural dynamics part get taught in at the graduate level. So usually, well, I took in my undergrad, but here in FIU, some other universities, they teach in undergrad if it's an elective course or something. And the thing is, you cannot be a tall building designer without structural dynamics. So tall building designer has to study lateral load resisting systems, has to study structural dynamics, have to study design of tall buildings because they have special design. So usually if you want to be a structural engineer specialized in tall buildings design, this is kind of the basics that you have to start with. Structural dynamics is a big class. Like it's, I'm not sure if you check the curriculum. In the master's, there is a structural dynamic class taught by Dr. Amal Awadi. So it's big, one semester class, you study, you solve a lot of problems. So I try to condense this class in 1 or 2 lectures for you so that you can understand the basics of that class. But before I do this, all of you took at least the structural analysis 1, right? Took it or still taking it, so 1, no structural analysis 1? Really? This 3rd year, right? But you are taking it this, are you gonna take it?
I haven't looked at that. I usually, I don't know.
And the basic structure analysis, like analysis of beams, of trusses, frames.
If that's mechanics and materials, then.
But at least some of you took structure analysis already. You have to. Nobody can graduate without structure analysis class.
Yeah, we have.
Yeah. So anyway, so based on that, structure analysis. Okay, let me talk a little bit about structure analysis. So to design buildings, first step we have to do analysis. And what analysis is? Analysis is that we need to find how much forces inside the structural member. Because you cannot design for forces that you don't know. So the first thing that you, like let's say, this is a column, like a column in the corner or something. And I want to design this column. The thing is, you will not know how to design this column without knowing how much force that this column is going to have. So basically, you need to find how much forces that this column is going to have. What is the value of B? All right? And the thing is, you will not be able to design the foundation without knowing how much reaction you are going to have here. All right? So that's what a structure analysis do. So structure analysis gets forces and deformation. That's the whole thing from a structure analysis. We need to know how much forces that our members are going to have and how much deformations that our member are going to expose. For example, if you have a beam like this, what beam means, probably you should know, but beams is a structural member that can take loads. Like let's say this floor, usually this is a slab system. It's called slab. It has all the floor loading. It takes our load, like my load, your load, chairs, live load, dead load, and distribute it, like take it, distribute it to the beams. Usually the beams is surrounded around this room, like here. Like let's say this. Let's assume that we are on the 2nd floor, okay? We are here. So basically this is slab, take all our load, and distribute the loads to the beams on the side. Okay, so all our loads, but the thing is the slab has to hold itself. So we have to design the slab to hold this load. So basically when you put load in this slab, what is gonna happen? This slab system is gonna make like this or both at the same time. All right, so I have to design this slab, it can take this bending. If the slab is not designed for this bending moment, it's gonna fail. So that's what a structure analysis is going to do. It's going to tell you how much bending moment this slab is going to take and how we can design for this bending. All right, let's say that the slab is safe and designed and take all the loads. So then the load is gonna distribute it on the beams around the slab. So the thing is, here's the thing. So if the load is here, where do you think most of the load is gonna go to? Is this beam or this beam? Load is always looking for the shortest, easiest direction to go to. So load is gonna go, oh, I'm gonna go, well, this beam is not gonna get zero, it's gonna get some load, but not as much at this beam. So load is gonna be distributed and goes in the shortest path. Usually, it's what we make is like, we make a 45-degree angle here and a 45-degree angle here, and these two lines are gonna meet, and then here and here. So mostly, this load goes that way, and all the load here goes that way, all the load here goes that way, all the load here goes that way, all right? So that's called load distribution. So the load get distributed, beams get their contribution, and then this beam has to be designed to take the loads that comes from the slab. So that's also what the structure analysis do. It calculates, like, let's say that this is our beam. I'm gonna take this beam, and I'm gonna study this beam here. Here, here, here. Now let's say this beam, usually we simulate distributed load something like this. We say that there is load coming on this beam, something like this. That means like small arrows that shows that the load is going down and it's distributed on the beam. So if there's a concentrated load, let's say I put a winch or I put like a big machine, heavy machine at a specific position. So we put like one line like this and I put P, that's called concentrated load. If there's a concentrated moment, I put a concentrated moment, something like this. If there is a triangular load, I put the triangular load, something like that, okay? So that's how we put the loads on our beams. All this load calculations is a structure analysis. So structure analysis, it's all about how you calculate the load. By the way, load calculations, that's a whole big science that includes statistics and includes a lot of stuff. Because the thing is, this slab doesn't have a constant deterministic load. Every day, there's different number of students. Maybe they are gonna convert this to a conference room. So we have to use the statistics to come up with a number that can make this system safe for the whole lifetime of the system. We don't wanna over-design it and we don't wanna under-design it. So I took a class during my PhD, it's called load modeling, just for loads, not structure analysis, nothing. It's all about how we can calculate the loads on systems. And this includes rain loads, snow loads, live loads, dead loads, seismic, wind, all types of loads. There is a standards, like a big book like this. It tells you how just to calculate the loads on your system, okay? So let's say that we know how to calculate the loads and we get the loads on our beam. That's where your structure analysis starts. They don't tell you how to calculate the loads. It's given to you in the problem. Oh, this beam has a load 2 pounds per feet, or 100 pounds per feet, or 2 tons per feet. So let's assume that you got this load. Structure analysis is all about calculating the reactions here. What is the value of the reaction here? What is the value of the reaction here? So that is the first step that you do in a structure analysis course. And then, this is called external forces. We use this external forces to design the column that is holding this. So this is basically the reaction. So this is an action on the column. So this column is having this as a load on it. So I need to calculate this reaction. And the second thing, for this beam to hold itself, we design it for bending moment, we design it for shear force, we design it for normal force if it has normal force. For example, if this beam has something that makes tension, like let's say this beam is in the desert, where the temperature goes low and high, and it's exposed to thermal expansion, so we need to design for normal force. This beam is exposed to this load, and this load is going to make this beam to bend like this. So we need this beam to take this bending moment, and we need to design for this bending moment. This beam can have a shear force. Shear forces means like this beam might crack that way. So we need to design this beam that there is no shear failure can happen in this beam. So structure analysis tells you how to calculate bending moment, how to calculate shear force, how to calculate normal force. This is what a structure analysis do. So usually you would, for example, like a beam like this, you would have like a shear force against something like this. The shear is high here because you have a big reaction here that makes a lot of shear, and then there's a load comes down, so the shear peak goes down until zero, and then negative, and there's a reaction to take the shear back up there. Bending moment usually, in all the world, we draw the bending moment down like this. It's how much bending this beam is made like this. In the US, we usually draw this up, something like this, but both are fine, just like the way that we draw bending moment. Anyway, so in a structure analysis, you learn how to calculate these forces. Some of them are external, some of them are internal. And also, I'm not sure if you learned how to do this or not, we need to calculate deformation. Like this beam, like this. I want to know how much deformation this beam is going to have. What is the value of delta? All right? That's all what a structure analysis do. I remember I took 8, 10 structure analysis class in my career. They are all about calculating internal forces, external forces, deformation, nothing else. That's the main objective of any structure analysis class. Maybe you're going to take advanced one. I teach advanced structure analysis in next fall. I teach students how to do the same thing, but for something called indeterminate structure. There's something called determinate, something called indeterminate. You'll learn trusses, beams, and frames. I'm going to teach you how to do it for arches and cables. I'm going to teach you how to do it for other structural systems. So at the end of the day, I'm teaching you different methods to calculate forces and deformations, and that's what all the structure analysis is about. Sometimes it gets complicated when you work with dynamic loads. All the loads that you deal with in undergrad is static. Like I'm telling you, this load is not a change. It's static, it's staying there, and it's not moving. All right? If it's dynamic, that's a completely different game, right? So in structure analysis, like for example, I just want to show you what the components that are having the load. Like here, you see the loads are taken by the slab, our load goes to the slab, and I told you that the load is looking for the shortest way to get transferred to these structural elements. So let's say that the beam took the loads. Where do you think the load is going to go first? Who's going to take the load from the beam? What is the beam supported with? What are the things that are supporting this system? The columns, right? So the load is going to be transferred to the beams, and the beams are going to take it and transfer it to the columns. And the column is going to transfer it to this column. By the way, the system in the second floor, this system, has nothing to do with the system. Like the load that transferred to this column is going to take it right away to the other column without passing to the system. What is going to happen in this system? The load is going to get distributed and is going to transfer it to the column. So basically, the column underneath, if there's another story underneath this story, is taking the load from this story and the other story. And each system is local, has nothing to do with the other system. I mean like the floor system. Like everything that happened in this floor has nothing to do with anything that happened in the upper floor. So the upper floor transferred to the column. The only system that is global is the columns. The columns, this column is holding the load from this column, and the load from the other column, and the load from the other column. So usually the columns is very, very important element. And it's a very significant element in the design. If it fails, like let's say for example, if this column failed, maybe the whole building is going to collapse. But if this beam failed, what is going to happen? We are going to have a local failure at this story that might not impacting the whole building. You are just want to need to repair just this story. Okay? So that's what all structure analysis is about, is to find forces and deformation. And as important as the find the forces, the deformations is also good. Like the thing is, I'm saying it's important. Why? Let's say that you design a structure and it's safe and it's gonna hold itself. But let's say I'm walking on this floor or I'm jumping on this floor and somebody in the other classroom is feeling vibration, is feeling deformation. That's not good. You want, it's called serviceability or comfortability. Like you need your structure to be comfortable and feel safe while being in it. Yeah, maybe while walking on it, it makes vibration. It's not gonna fail, but it's not comfortable for me to live in the system. So the codes puts some limit on the amount of deformation that the structure are gonna expose. Even sometimes when you design for forces, it gives you that this structure is gonna say, even it makes this deformation, but it's not comfortable to live in. So that's why we put some limitation on the deformation. Every time I design a structure, I check the deformation mid-span here, because the deformation is maximum here. And there is a code that tells me, is this delta is more than the allowable or no? If it's more than the allowable, that means I have to increase the thickness of the slab, all right? So that's why structure analysis help you to calculate forces, calculate deformation, so that it can help you with the design. So that's why you always learn structure analysis and then take design class, because the design class, first before you solve a design problem, you do structure analysis, get the forces, and then apply the design code, okay? All right, so that's around 20 minutes introduction to what is structure analysis do, and that's actually really important. Sometimes you study structure analysis without getting all this introduction, and you don't know why you are getting forces and why you are calculating deformation. This is why you are doing structure analysis, so that you can use it in design. So right now, we know why we are doing structure analysis, okay? So let's move to structural dynamics. But before I move to structural dynamics, I want to just make a little bit of introduction about springs. I told you before what does springs do, but let's, all right. So I told you before, in our field, we usually model every element with springs. Do you guys remember, like sometimes in a model, like let's say, I did this problem before, like I had a bar, and this bar has a collar, and this collar is attached to a spring, something like this. So this is a direct spring, like a real spring. But the thing is, sometimes in our structure analysis models, when you do thesis or you do research or something, this column here, we model it as a spring, like this. And if we want to model like a beam like this, and we want to understand the behavior of this beam, we represent the stiffness of the beam with a spring. How? Like this point, I represent it by a spring that way, and another shear spring that way, like connected by this beam, and maybe another, I want to draw another spring, like a rotational spring that way. That's how we can understand the performance of the beam. So every element has a stiffness, all right? Like let's say, let's talk about the stiffness a little bit. So the stiffness, do you guys remember K? That's the stiffness of the spring, but that's only axial stiffness. If you have any structural member, it can have different types of stiffness. It can have axial stiffness, how much compression it can take. It can have shear stiffness, how much shear it can take. It can have torsional stiffness, how much torsion it can take. It can have bending stiffness, how much bending it can take, and also depends on the direction. There's shear that way, and there's shear that way. But at the end of the day, they are all shear stiffness. So stiffness is not only like one component, can be multiple components. Depends on what are you looking at, all right? So members can have multiple types of stiffness that you can look at the same time. But we need to know how we can understand if a bunch of stiffness is acting together. Like let's say this floor is supported by 5 columns. Each column has different stiffness. How we can find the whole stiffness for the whole story, all right? So, do you guys remember Hooke's law? If you have a load P like this, applying on this column, and this delta happen, can you guys tell me what is the stiffness of this column? Okay, do you guys remember B equal K times delta? All right, so if B equal K times delta, what is the value of the stiffness K? B over delta. Actually, that's how we find the stiffness of the elements in the lab. If you want to find the stiffness of any element in the lab, take this element in the lab, put load on it, see how much delta is gonna take until it fails, and then divide the amount of B that you reached, divide it by delta, that's what's gonna give you the stiffness. If you wanna find torsional stiffness, take this element, apply torsion, and then see how much rotation is gonna make until it fails, and the amount of moment that you applied on this element, divide both of them on each other, you are gonna get the torsional stiffness. Like you are gonna get that M equal to K torsional times theta, so K theta is gonna be equal to M over theta. So this is how we can find the stiffnesses in the lab. So right now we understand what a stiffness is. Yes?
So for theta, would be like, degrees on like a compass or something, or would it be like a value itself, like meters?
The stiffness?
No, line theta.
Yes, you can have a degree or radian, whatever, but usually when we do it here, it's radian. All right. Okay, so that is the stiffness. The thing is, I want to teach you, if you have multiple stiffnesses connected together, how you can find the total stiffness of a specific element. All right, so let's say I have two systems. I have, this is my verse system. I have one stiffness, two stiffness, and another third one is connected. This one has K1, this one has K2, this one has K3. And you start, at this point, you start to pull with a force, B. All right, and I'm asking you to find what is the total stiffness of the system. Imagine this system is a bunch of bars, like, that has different size, and you apply it with a B here, and you want to know what is the total axial stiffness of the whole three bars together. So how we can find that. All right, let's take this system and understand it. Once you pull all the system with B, they are all gonna make a delta, right? They're gonna be having a delta. This delta is coming from this one makes some delta, and this one makes some delta, and this one makes some delta, plus all of them together is gonna give you the total delta. So the total delta is delta equal to delta 1, like this one is gonna have delta 1, this one is gonna have delta 2, this one is gonna have delta 3. Are all of them equal? If they are all the same stiffness, maybe they are gonna be equal. But if they are having different stiffness, the strong one is gonna have less delta, right? If this one is very, very stiff, it's very easy to one. Like let's say that you have a steel and you have aluminum and you have rubber. Which one is gonna expose more delta? The rubber one, right? Okay. So it's delta 1 plus delta 2 plus delta 3. But you know what is special about this system? That they all have the same axial force. Why? The thing is, how to find axial force? Cut in this section and see how much forces you have here. You have B, right? Cut in this section and see how much force you have here. It's B. Here, it's B. And actually you can do it from this side. There's a reaction B. So if you cut and look from the left, it's only B. So all of them has B. This one has B, this one has B. They all are exposed to the same axial force. So if you want to find delta 1 is going to be equal. Here, I have the rule. Actually, this one, delta is going to be equal B over K, right? If you have B equal K times delta, so delta is going to be equal to B over K. So delta 1 is going to be equal to B over K3. Sorry, this is delta 3. So let's put 3 and 3. And here, delta 2 is going to be equal to B over K2. And here is going to, interesting. So I name them, let's make this 3, and let's make this one. Delta 1 is going to be equal to B over K1. Do you guys agree with me on that? All right, they all have the same B, but they all are exposing different deltas, and they all have, because they have different stiffness. So if you want to find this, we can substitute with this here. So the total delta is going to be equal to delta 1, which is equal to B over K1, plus B over K2, plus B over K3. And the total delta actually is equal to the total B over the K equivalent of the whole system. right? Because delta is equal to B over K. So if you were able to sum all of this, this is gonna be equal to B over the K equivalent. So if you wanna find the value of K equivalent, you can divide all of this over B, so all these B's are gonna be gone. So 1 over K equivalent is gonna be equal to 1 over K1 plus 1 over K2 plus 1 over K3. This system is called barrel stiffness system. So let's put 1 system. Sorry, that's a series of stiffness. Series stiffness. All right, series because they are in series. Does anybody have any question? So that is the first part. So let's say in an exam, midterm, I give you a system like this, and I give you every stiffness. I told you the stiffness here is 1,000, and here is 500, and here is 300, and they are having 10 kilonewton B. Find the equivalent, and actually I don't have to tell what is the value of B. I can tell you what is the equivalent stiffness. So we're gonna say 1 over K equivalent is gonna be equal to 1 over 1,000, 1 over 500, 1 over 300, and then you plus all of them, flip it, is gonna give you K equivalent. I can give you B, but I'm gonna ask you what is the total delta at the end. So if I give you B and I told you what is the total delta, you divide B over K equivalent. All right? So that's how you are gonna solve an exam. Okay? All right. What if my stiffnesses are in series? Sorry, are in parallel. So for example, I have my first stiffness is something like this, the second, the third, and they are all connected to a wall, and there's a very rigid body here, and I'm applying a load B pulling from here. And this is K1, K2, K3, what I'm supposed to do. So how I can find the equivalent stiffness of this system. All right, let's see what is special about this system. What is special about this system, once you pull this body out, all these stiffnesses are forced to move with the same delta. All right, because this is a very rigid body. So it's all, we all move together or nobody's gonna move. It's the opposite here. The opposite here, that everyone has different delta, but they are all having the same B. But what's happening here, this one is having B1, this one is having B2, this one is having B3. And if you sum B1 and B2 and B3, it's gonna give you B, because this is how the force got distributed at each one of them. All right, I'm gonna ask you, which one that takes more B? The one that has more stiffness, because it has more resistance. Like for example, if you have a column in this corner that is really, really stiff, and the thing is, it can hold the whole system. All right, let's say if there's a column over there, this column is taking very, very minimal amount of load. If it fails, all the load is gonna be transferred to this column. If this column is not stiff enough, the whole system is gonna fail. But if this column is very stiff, it can take the whole load. All right? Okay. So let's see how we can calculate the equivalent stiffness. I'm gonna start with that B equal to B1 plus B2 plus B3. Because B is gonna be equal to all the B's that got distributed here. And if you wanna track how's can you guys tell me if this is the direction of the force? If this is springs are in tension or compression? Tension, right? So what happened is, this one is gonna apply that way, and here, that is gonna be that way, and the reaction here is gonna be that way. This floats, this P, and this is external forces. This is internal forces, you cannot see it. It happens inside the spring. How we can call its tension, if it's pulling the joint, it's tension. Like if this is the joint and it's pull the joint, it's a tension. Same thing like trusses. When you guys used to work in statics or structure analysis and you have a truss like this, if the truss force is going that way, the internal force, this is a tension force. How do I know? Because it pulled the joint. If it's going that way, that's compression, because it compressed the joint. You are like pushing the joints down. All right. B1, B2, B3. This is the total force. And I know that from Hooke's law that B is equal to K times delta. So basically I can say here, this is K1 times delta 1 plus K2 times delta 2 plus K3 times delta 3. But I told you the special about this system that they all have the same delta. Delta 1 equal to delta 2 equal to delta 3 equal to same delta. All are they gonna move here. So basically I can divide over delta. You all are gonna be gone. But the thing is, I have here, but before I cancel these, I have to have here K equivalent times delta. Like the final B is gonna be equal to the K equivalent of the system times the delta of the system. So when I divide over delta, this delta is gonna be gone. You guys agree with me? And then at the end, the K equivalent is gonna be the easiest equation ever. K equivalent equal to K1 plus K2 plus K3. That is the equivalent stiffness of the system. So in any structural system, if you found that the stiffness of the elements are in parallel, plus the stiffnesses right away. Like if this is 100, 200, 300, the total is gonna be 600. And basically, if you have a stiffness equal to K equivalent, and you're pulling it with the same B, it's gonna give you the same delta. Like let's say this is 100, 200, 300. So if this is a 600, and it's getting pulled by the same B, it's gonna give you the same delta. All right? Okay. You're gonna ask me why I'm learning how to get the K equivalent, because this is actually the first step for simplification of a structural system. And we are gonna see this really obvious when I do this on a building application. All right, so let's say I have a multi-story building, and this building is something like this. I'm looking from the side view. This is the ground. Floor system, okay? And this is the ground. All right, the thing is, dynamically solving this structural system, and manually, like by hand or even on a software is gonna be easier, but solving it manually or doing analysis manually on a 3D building like this, that is gonna be really, really difficult. So usually, engineers or scientists, they tend to simplify the models. So we need to simplify this model and try to make it, oh, it has how many columns? I have 1, 2, 3, 4, 5, 6, 7 times 4. It's gonna be like 28 columns. And by the way, this is a side view. Like you might have this repeated, so you might end up with a building that has 100 or 200 columns. And dealing with all these numbers of components is really overwhelming, and actually is gonna make your equations much bigger. So we usually tend to reduce the system. I wanna reduce this system to, let's say, I wanna make all these columns one column. Like I'm gonna make it like something like this. This is the slab. I'm gonna represent the slab. The slab actually has the biggest mass in the structure. The biggest mass in the structure is the slab system, 90%. So usually in tall building, when we design tall buildings, we use lightweight concrete to reduce the weight of the structure. So we use lightweight concrete is like, I don't know, you guys know the gamma of the concrete? It's around 2.4 ton per meter cube. If you use lightweight concrete, sometimes you can reduce this to 1.8, so you reduce the weight of your whole structure. So usually we can represent a slab with a mass. This is mass number 2, mass number 3. This one, and this one. All right? So the thing is, right now I moved it from the 2D, actually I moved it from the 3D to 2D, and from 2D to like 1D that has multiple masses and stuff. So basically, this is K equivalent of story number 1, this is K equivalent of story number 2, 3, 4, 5, up to K equivalent of N. So what I want to do, I want to take all these columns and try to find what is the stiffness equivalent of these columns. If I want to plus all these columns together. The thing is, I have to understand the behavior of the system. Let's say a seismic load hit this building. Do you guys know where the seismic load comes from? Or what is the difference between wind and seismic? Wind happens above the ground. You have destruction in the air, and the air moves really fast and push the building from the superstructure. Seismic, something happened under the ground, shake the ground from down, and basically it's like somebody is holding the foundation of this structure and shaking it. You know, somebody's like coming from your feet and it starts shaking your feet. That's what happened in seismic. So usually we put the seismic load something like this, all right? We call it F base, force at the base. All right, so let's see this structure take this force, and basically this structure is gonna have a deformation like this, something like that. This story is gonna go all the way here. This one is gonna be here, 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 and here, okay? All right, I want you to tell me, how much deformation is this column is gonna have? Let's say this is delta 1. This column is gonna move delta 1. How about this one? Delta 1, right? Why? Because the slab system is a very, very rigid system. It's like holding all this column. We either all go together or we are not gonna go together. So it holds all the column in the floor system to go in the same direction, unless if the slab system, we call it flexible diaphragm. Flexible diaphragm, if the slab system is very thin and has many openings, that make the slab system is not rigid to move all in the same time. But if you have a rigid slab system, they all are gonna move together. These still are gonna move, but I mean like if it's a flexible, but not with the same deformation. But let's assume you all are gonna make the same delta. Remember, if you have a system that having all the same delta, is it stiffness in parallel or stiffness in series? Parallel, right? Like the same thing that happened here. All the stiffness are exposing the same delta. So if these columns are all having the same delta, you can say that the K equivalent of them is equal to K1 plus K2 up to Kn. Same thing here. You can get this one, this one, this one, and you can get all the Ks. All right? Okay. So once you do this for every floor, what if I want to do a second level of simplification? I want to represent all these columns and all the story with just one big giant column and one big mass. Something like this that has the K equivalent for all the 200 columns in the system. Look at that. This is the delta of one floor, right? What happened in the next floor is equal to the delta from the second floor plus the delta that happened in this floor. And this one has the delta from downstairs to this floor, and this one, and so on, right? So basically, this floor is gonna move, it's gonna take the second floor with it, and the second floor is gonna make its own delta. So that's exactly is equivalent to what's happening here. If you wanna find the total delta, here, you have to sum the delta here, and this one, and this one, and this one, and this one is gonna give you all the delta here. So that's a barrel stiffness. Why? Because the final delta of the system equal to the delta that comes from system 1 plus system 2 plus system 3. So I can say that K equivalent 1 and K equivalent 2, 3, they are all parallel or series? Series, right? Because they are in series. The thing is, here, this delta from this floor, like this one, I'm gonna put it here. This is delta 1, and the thing is, what happened here? This is delta 2. Because the thing is, let's say the delta happened at the versa floor only, and there's no other delta. So basically this building is gonna have delta like this, and all the building is gonna be like this. But what happens, they accumulate delta one on top of each other. So here's delta one, and here's delta two, and here's delta three, delta four. And that's actually what matters, you know? If you're building, there's an earthquake, and your building make a pure translation, like moved like this without any bending, I don't have any problem. There's no internal forces are gonna be developed. There's nothing is gonna happen. The thing is, the only thing that happens to structural system, like let's say you are having a fixed member, and you hold it like this, and you move both of them that way. Can you guys tell me what is the reaction on the internal forces here? Zero. Because you didn't do any bending, or you didn't apply any compression. You just hold your member from here to here. But if I told you I made like this, there's gonna be internal force. But if you hold it like this, nothing's gonna happen. But if I made it like this, something's gonna happen. So that's why there's a science for, in seismic, it's called base isolation. Like sometimes they do the foundation on rubbers or something. It makes when an earthquake happen, they make the building move in a translation way that doesn't cause any bending. So you isolate the base, and when the seismic house you're building is gonna make like this. If your building is made like this, pure translation, there is no internal forces is gonna be developed in your structural member. All what happens is this, what we call it, the differential deformation, or let's say you have this frame, and this frame on a hinge and another hinge. If these two hinges make settlement with the same value, like let's say this is went 2 centimeters and this is went down 2 centimeters, like this, there's no internal forces are gonna be developed. What is gonna cause damage if one of them made settlement? Like this one is holding itself, and this one is like, is settling down, so it's gonna cause cracks. But if you take the whole building and move it here or move it there as a one piece, it's not gonna make any damage, right? Okay, that's what happens here. So this one is a pure translation. All this moved that way, and this is the only delta that happened in this floor. Same thing here. That is the differential delta that happens in each floor. So if you want to find, this is K equivalent, if you want to find the K equivalent, you have to use the series stiffness equation, this equation, to find the K equivalent of the whole system. So this one is going to be equal to K equivalent is going to be equal to 1 over K equivalent 1 plus, oh sorry, this is going to be 1 over K equivalent is going to be equal to K equivalent 2, so on up to 1K equivalent N. So if you take this and this, all of these, and take 1 over this, 1 over this, and 1 over this up to K equivalent N, this is going to be equal to 1 over the total K equivalent of the whole system. And this is going to be the mass of the whole system. All right, so what I did right now, I developed 2 simplified systems from a big building. If these 2 systems got exposed to the same amount of force at the base, FB, and this one is going to expose to FB, this one is going to expose delta, and this one is going to expose delta, and this one is going to expose delta, and the 3 deltas are equal to each other. So that's what we have done right now. Simplification of the system. So why did I do simplification of the system? Because that is much easier to deal with. Okay, did you guys got that? All right. The thing is, usually when we do analysis for our buildings or our structural system, there's 3 components that contributes to your equation of motion of your structure. First, the mass. Second is the stiffness. The more the mass is, you are dealing with a lot of load that you have to handle. Stiffness is the one that's contributing to the rigidity of your structure, so that's also important. There is another thing is called damping. What is damping? Damping, we usually represent damping with something like this. Like if this is the stiffness that holds the structure, we make something like this, like the piston of the car, something, it's called dashpot. And this system, we give it letter C. And this component, we represent the way that, we can dissipate the energy of the earthquake through things in your structure. For example, let's say your structure, sometimes we put in our structure something like this. You make a truss, and this truss you put like a hydraulic system here, something like that, and all the truss member. So when a seismic happens, this force is gonna be dissipated in the hydraulic movement that happened in this system. So this is called damping system. Sometimes, I'm not sure if you guys looked at Taipei 101 building, it has a water tank. That's also sometimes building use. Like Taipei 101 is a building that has like a big bowl of water on the top attached to some mechanisms. So basically if the earthquake or the wind pushing the building that way, the tank goes the other way. And if the building gets pushed this way, the tank goes the other way. It's basically, that's a way to damp the lateral loads. And actually, buildings sometimes have naturally damping methods to damp the force. Like every time a connection is open in a building on a crack, that's a damping force. So there's some force is released in friction. Even in a steel building, when you have a bolted connection or a welded connection and the connection opens and closes, there's a damping energy is released in the heat and the friction that happens in the connection. So that's why we represent this with something that's called damping coefficient. So let me ask you, damping is helping the structure or against the structure? Help the structure. Stiffness is helping the structure or against the structure? Help the structure. How about the mass? If you increase the mass, is it helping the structure or against the structure? Against the structure. So the better I reduce the mass and increase the stiffness and increase the damping. All right? So that is the three components that we deal with in the structural dynamics. The structural dynamics, it's all about mass, stiffness, and damping. All right? And the good structure engineer that makes the massless by using new technology like lightweight concrete, whatever. Sometimes people use, I'm not sure if you guys heard about hollow core slabs. They make slabs that has some hollow parts to decrease the weight. Sometimes they use lightweight concrete. Sometimes they use a steel, whatever, like materials that makes the slab is less to decrease the mass. The damping, that's many ways. You can include it by using dampers, you can use water tanks, whatever. The stiffness, that means you have to make your members more strong. So in tall buildings, we don't use regular concrete in the columns. We use something that's called high performance concrete or ultra high performance concrete. Concrete has a compressive strength double and sometimes triple the regular concrete. So that's why how we increase the stiffness. But let me ask you something. Do you think it is, I want to say, is it like right or is it like good that I use high compressive or ultra high performance concrete in the slab system? No, because the thing is that's a floor system that is making weight, so I don't want to spend more money on it. I spend more money on this column that holds sometimes 60 or 100 stories above. Usually when we design this column, like if you use normal concrete, this column may be like 3 meter by 3 meter, like a size of your bedroom. But if you use ultra performance high concrete, it can be 1 meter by 1 meter, okay? All right, so let's actually put all this into equation. Let's look at our building, which is gonna be this one, by the way. So right now, this building, when I draw this, K, C, and M. What this is gonna represent moving forward. This is a building, right? You guys know how did I come up with this? It was that, and then we transform it to this, and then we transform it to this. It had an equivalent stiffness, an equivalent this, and mass equivalent. So it has all the equivalent masses, the stiffnesses, and damping coefficients. So, and the thing is, this is my system, is like safe and is enjoying his time, and then one day a seismic is gonna hit this peaceful, human being. All right. So here at B. So you have a resisting systems and you have a forcing systems. So let's see how we can deal with this as a dynamic system. All right, I'm gonna put it that way. I'm gonna put my mass like a box here. And this mass is on a roller, something like that, M, okay? And this mass M is attached to a spring, has a stiffness K, and also attached to a damping or a damper, something like this, and all this holding from here. Let's connect them together, all right? And then one day, this system got hit with a force F. And by the way, the seismic force is not a constant force normally. It's like something, it's usually not like FB. Usually what happens is the ground shakes, all right? This is time, and this is the acceleration of the ground. The ground is like zero, the ground is not moving, and then one day seismic hit, and then the ground acceleration start making like this until it gets a peak and then dies down. That's what happens in earthquake. In like 5-6 seconds, your building is gonna make this and come back to original place. In less than a minute, that's what happened in earthquake. So the acceleration of the ground is like moving little by little, and the thing is, it moves positive and negative, so it goes up and down, and then at some point it's gonna peak, and then the peak keeps dying out until it becomes zero. Did you guys got that? And this is the ground of the acceleration of the ground. If you want to find FB, FB equal the mass of your structure times the acceleration of the ground. This is kind of a simple way to find the FB, but we don't calculate it that way, but this is, you can imagine it that way. Anyway, so we can say that FB is function of T because over time, the structure has this force, this force, this force until it comes to the big force. So this is F function of T because the acceleration is function of T. So that's a dynamic system. We can use Newton's second law to solve this system, that the summation of the forces on this system, summation of the forces equal the mass times the acceleration of the system. So basically, this system is gonna move that way, assuming, I'm gonna assume that this system is gonna move that way, and this is the MA direction. So if you wanna find the acceleration, you have to find out you have to solve this equation. So let's find out. I assume that this is my positive direction. So let's find all the forces that act on the system. So the force that act on this system, first I have the stiffness. If this building is gonna move that way, this spring is not gonna let this building move that way. You have something that's very stiff holding this building. And the force is equal to K times delta. If this building moves the delta, I'm gonna name it U, like A. We can keep it delta, or basically I can say delta is gonna be U, and delta and the velocity is gonna be U dot, and the acceleration is gonna be U double dot, so that we can be consistent. Because delta is the same like how much displacement, and the displacement is gonna be U. So let's remove delta and put U, all right? So right now, I wanna know how much displacement, how much U that this building made that way, and multiply K times U is gonna give me how much force is here. How about C, the damping coefficient, the damper, C here. The damper also hold the building from moving. So the force in the damping is function of U dot, the velocity. Like the same thing that we say that the force is proportional to delta, and the proportionality factor is K. The force is proportional in C, or is proportional with the velocity, I'm gonna say V, and the proportionality factor is the damping coefficient. And also the force is proportional to the acceleration, A, and the proportionality factor is the mass. So P equals mass times A, B equals K times delta, B equals C times V. So they all are gonna give you force. All right, so you have Cu dot, Ku, and you have a force here. So basically you can say, and I can actually remove A and put U double dot, because A is the second derivative of the displacement U. All right, so the equation here, sum of the forces equal to the mass times the acceleration is going to be equal all the forces. So I have this force equal to negative Ku, because it's in the negative direction, minus Cu dot plus Ft, because I have the force of the earthquake, is going to be equal to the mass times the acceleration. Is that right? All the forces on the system, I have to be careful with the sign. I assume this is my positive sign. So these two are negative, that way, this one is positive, and all of them are going to be equal to the mass times the acceleration. By the way, this is the free body diagram. This is the kinetic diagram where I have the direction. So let's arrange this equation. Arranging this equation is going to give us, by the way, I can remove acceleration, I can make it u double dot, like I can make it that way. I can say that m u double dot plus c u dot plus k u equal to f function of time. So basically I'm gonna send these two this side and leave this part alone. And it's gonna give you one of the most important equations in the engineering dynamics. I never forget this equation. And this is gonna be in the second midterm, so you focus. So this equation, let me write it here, m u double dot plus c u dot plus k u equal to the force F T. All right, have you guys seen equations like this before that has u dot and u double dot? We call it something, and definitely you guys had it in math. Differential equation. And what degree is this equation? Second degree. Why it's a second degree? It has double dot. So this is a second degree non-homogeneous equation. Why? Because this is not equal to 0. If this is equal to 0, it's going to be homogeneous equation. So this is a second degree differential equation. Do you guys remember how we can solve this equation? I'm not going to solve it, but you should be able to know how to solve it. Basically, you assume u equal to a sine theta or a cosine theta, and you differentiate, then double, and you try to substitute, because the solution of any equation is a function in sine and cosine. So it's gonna take, I believe I can spend 6 boards to solve this equation. I can't give you the solution, but I'm not interested in solving it. But I'm interested, what is after solving this equation? So, but before I do this, I want to tell you something. This part of this equation here, this part, it's called the resisting function. And this part is called the forcing function. So maybe in the midterm, I'm going to ask you, write the equation of motion of structural dynamics and show me where is the resisting functions and where is the forcing functions. So this is the resisting functions and this is the forcing function. I'm going to ask you to show me the free body diagram of the forces on the system. So I might give you something like this, and I ask you to convert it to the first simplification and the second simplification, and ask you to draw the free body diagram and to show me, using Newton's second law, how to come up with the structural dynamic equation of the system. Okay? Are we okay with that? Does anybody have any questions so far? All right. I told you I'm not interested in knowing how to solve this equation. However, you should be able to solve it. Like, go back to your basics, see how we can solve an equation like this. It's going to be u equals something in sine and cosine. But let's say I found the value of u, because what is the result from solving this equation? I need to find what is the value of u. Can you guys tell me what is u? in all this?
The displacement.
The displacement of the structure, that's, I told you, that's what is the structure analysis one. We need to find, I just changed delta and I replaced it with U. And that's what all the structure analysis is about. It's about finding the deformation of the structure. So once you find U, you are gonna be able to know how much this structure made deformation during the, from the seismic load, right? But the thing is, I wanna ask you, is this deformation constant? Why? Why it's not constant?
Because the force isn't.
Because the force is not constant, the forces keep changing over time. Definitely, when the seismic is happening, you are having little deformation. And when the earthquake peaking, you are having big deformation. So this is actually very difficult to solve because F is function over time. So you have, if you want to solve this equation, you have to divide this into pieces. Where's the seismic curve that yeah, here. So you have to divide this into pieces and solve this equation piece by piece. So basically we program this equation and we make a for loop, and the for loop from time equal to 0, and go through each time step and solve the equation and get the value of the displacement at each time step. Because the load is not constant. If the load is constant, it's gonna be a dynamic problem. But if the load is varying over time, it's, if the load is constant, it's a static problem. But if it's varying, it is gonna be a dynamic problem. So solving this structure, where's the, so if you solve this equation, let's put it here, M U double dot C U dot K U equal to FT. If you solve it, by the way, FT is something like this. This is your input. Is something T, and it's gonna be something like this. So your result, U, is gonna be something U over T. Sorry, this is U, and this is T. And you are gonna end up with displacement something like this. If the force is varying over time, the deformation is going to be varying over time. And if you try to find the velocity and the acceleration is going to be the same thing. So time, and here u dot, and here time, and here u double dot. So you're going to find them something like this. We use something called Duhamel integral to solve this equation. Basically, you divide it into steps and you integrate all over the steps to come up with the final one of these. So I don't care how to solve it, but I care about how the results look like. So at the end of the day, you are gonna have a deformation something like this. And by the way, this deformation is here at the end, at the tip. The final delta that this system is making. And to be honest, I'm not interested in this small values. I'm interested in the maximum value here that is gonna make a maximum damage. And the same thing, the maximum velocity and the maximum acceleration. So right, I'm gonna stop here for now, but we are gonna find next time how we are gonna use this displacement to find or to come up with a generalized curve that can tell us how much displacement that every structure can make based on the structural mass and stiffness in them. Alright, see you guys next time.
It was fun. I really liked it. I was thinking about you.